to have Kenkichi Tsunoda from Kyushu University to give this talk about large deviations and mixing times for a reaction diffusion model. Kenkichi, please start.
Yeah, thank you very much for your introduction. I'm Kenkichi Tsunoda from Kyushu University. First of all, I'd like to thank organizers for giving me an opportunity of this talk. Today, I'd like to talk about this topic. Today, I'd like to talk about a scaling limit or a so-called reaction diffusion model, which is also known as Glauber-Kawasaki dynamics. And especially, I'd like to focus on large deviations and mixing times for this model. Okay. And recently, I have moved to Kyushu University. Yeah. Anyway, okay, let me start my talk. Yes, this is a table of my talk. At the first part, I'd like to introduce this model, and I'd like to give you a very brief explanation about this model. And after that, I'd like to explain some phase transition phenomenon for this model. It is a direct consequence of our large deviation principle, which is established in this paper. And to prove this large deviation principle, we need another large deviation principle, which corresponds to a large deviation principle from hydrodynamic limit. Yes. And these results are not so new, but today's main topic is this one, mixing times for this model. So after this study, I have wanted to study this phase transition in terms of mixing times. So this is the main topic of this talk. And the main results of this talk are the following. So in the high temperature regime, this model exhibits a rapid mixing or fast mixing. This result is due to my collaborator with this result is due to our work with my collaborator Kenkichi Tanaka, and this result is still under review. And at the low temperature regime, we can say that this model exhibits exponentially slow mixing, and this result has been published from ALEA recently. After that, I'd like to give you a very brief sketch of these proofs. This is the content of my talk. Oh, sorry. No. Okay. Okay, let me give you an introduction of this talk and of this model. So we consider so-called reaction diffusion model, or so-called Glauber-Kawasaki dynamics, which is an exclusion type particle system. So we consider a superposition of two different dynamics. The one is the exclusion process, and the other is Glauber dynamics. So we superpose two different dynamics on a one-dimensional periodic domain. So, and because we consider an exclusion type process, the state space is given by this one. So we denote its element by eta. So eta is just a correction of eta x. Eta x is indexed by x, and it is Tn is just the 1D torus. The system size is equal to n. The interpretation is the following. So, so eta x is equal to 1 if there is a particle at site x. If not, we read that there is no particle at site x. This is the meaning of the configuration eta. This is the usual interpretation of this configuration. So the model is described as follows. So we have two different dynamics, as I said. So the one is a symmetric simple exclusion process, but it is accelerated by n squared. So it corresponds to a diffusive scaling. So there are several particles like this. So, and this particle can jump to the right or the left with equal probability. But if there is another particle like this, then this jump will be suppressed. So this is a very well-known interacting particle system known as an exclusion process. But we also consider the Glauber dynamics, which correspond to birth and death dynamics of particles. So there is particle, there are no particle, there is particle like this. So here at this site, there is no particle, but at this site, sometimes some new particle will be created like this, and its jump rate, its jump rates depends on the configuration around X. And we also have an annihilation mechanism. So here at this site, there is a particle, and this particle is sometimes will be annihilated like this. So this is the evolution of the Glauber dynamics. Yes. And if we want to define this dynamics more precisely, we need to introduce our Markovian generator on this on this state space. So here, this f is just a function on the state space. So Ln is just so Ln is just the sum of n squared times Le and Lz. So Le corresponds to the generator of the symmetric simple exclusion process on the 1D periodic torus, and Lz is the generator of the Glauber dynamics, and its jump rate is determined by Cx eta. So, and I'd like to focus on a particular jump rate on C. So let us introduce this jump rate C. So for an inverse temperature beta, we introduce this transformation. So this transformation frequently appears in the study of the Ising model. Anyway, gamma is determined by this transformation, hyperbolic tangent of beta. Okay, let us fix this gamma. So gamma is just between 0 and 1, and we consider this a bit complicated, but not so bad jump rate Cx eta. Because, okay, our generator is given by this one, Le plus Lz, and let us forget about the exclusion part, and let us consider the Glauber dynamics with this jump rate. Then the invariant measure is given by our usual Gibbs measure related to the 1D nearest neighbor Ising model. So this jump rate is not so bad, and in some sense this is natural, and I'd like to focus on this jump rate for simplicity of my presentation. Of course, we can consider much more general jump rate C, but I'd like to focus on this C in this talk. And this model has been introduced by Dumas, Ferrari, and Lebowitz in 1986 to study a very famous partial differential equation called reaction-diffusion equation. So if we don't have the reaction term, then this is nothing but the heat equation. But we have this force term or reaction term like this, and they have introduced this model to study this reaction-diffusion equation from a microscopic point of view. And sorry, if you have any question, please do not hesitate to ask me. Yeah, anyway. And so, yeah, this is a motivation to study this model. And anyway, so the limiting reaction term is determined by a microscopic jump rate, C. So C is the jump rate for which governs the Glauber dynamics. And here, neuro is the Bernoulli product, Bernoulli images. Bernoulli images. So, and we can easily compute this expectation. And f is given by this formula. And it is just a polynomial in rho. And we have this here, rho here, and rho squared here. So f is just cubic polynomial in rho. And f is called a potential. So f is just one of primitive functions of f with minus sign. And we give it like this. And the shape of V is given as follows. So if gamma, so the parameter gamma is less than or equal to 1/2, then, or less, if gamma is strictly less than 1/2, then its shape is given by this one, sorry, this one, correspond to this case. So gamma equal, if gamma is 1/4, then the graph of V is given by this one. So it is a singular potential. For the case gamma equal to 1/2, then the potential V is given by this green line. So in this case, at the bottom of the potential, and the Hessian of the bottom vanishes. So it is degenerate in this case. So therefore, this is in some sense critical. On the other hand, if gamma is larger than 1/2, then there is a the potential becomes a double potential like this. So we can see the difference like this, change of the values of gamma. Yes. And I'd like to tell you the precise result obtained by Dumas, Ferrari, and Lebowitz. For this purpose, I'd like to introduce the usual empirical measure, which express the density of particles. So empirical measure is defined by this formula. So for each configuration eta, we define a measure on a continuum torus. So we regard each particle as a Dirac measure concentrated at this site with mass 1/n. So this is a measure on the, pi n is a measure on the torus. And then recall that we have accelerated the exclusion part by n², and so this corresponds to the diffusive scaling. And there is no speeded up factor in front of the Glauber part. And we know that this is a correct scaling. And we can observe a non-trivial evolution in the limit. And we substitute this eta. Sorry, eta Tn is so eta Tn is a Markov process generated by this Markovian generator. So we substitute this eta Tn into this eta. So this is a random measure or a random evolution of measures on the torus. And then Dumas, Ferrari and Lebowitz proved the following result. Okay, let us assume that at the initial time t, at the initial time, at time 0, we assume this convergence. So at time 0, we assume that the empirical measure converges to some measure which is deterministic and absolutely continuous with respect to the Lebesgue measure, whose density is given by some measurable function rho 0. Then they prove that this convergence propagates to for any t. For any fixed t, we have a similar convergence. So this is a random variable, but it converges to a deterministic measure whose density is given by the unique weak solution of the reaction diffusion equation. And of course, this is also called a hydrodynamic equation. So they obtained this result. Yes. And at this slide, I'd like to explain you several features of this model. So note that because we have the Glauber dynamics LZ, so we can easily see that this Markov process is irreducible because the total number of particles is not fixed. So, and the cardinality of the state space is finite. So, by a fundamental result on Markov processes, we can say that there is a unique probability measure, probability invariant measure. So there is a unique probability measure which is invariant under the dynamics, and we denote it by mu n. So because eta Tn is a Markov process on this state space, so mu n is just a measure on this configuration space. Okay. So we are interested in this mu n, and I listed difficulty of analyzing this mu n. The first one is that the system is nonlinear. So because the hydrodynamic equation is the reaction term is nonlinear in general. In this case, this is cubic in law, so it is nonlinear. In this sense, the system is nonlinear. And we also have these two difficulties. So the first one is that there is no explicit formula except for some special cases. So mu n is neither Bernoulli nor Gibbs. So, but for each marginal process, LE or LZ, for exclusion processes, Bernoulli measures are ergodic measures if we consider this process on a fold domain. And for the Glauber dynamics, LZ, Gibbs measure related to the Ising Hamiltonian is an invariant measure for LZ. But for the superposition of two different dynamics, we do not have an explicit formula for mu n. And in general, this measure is not reversible. So these are difficult to analyze this measure. I think these two features, these properties are common properties for non-equilibrium stationary states, and which have been studied in macroscopic fraction theory developed by Claudio and his collaborators. Anyway, we have some motivation to study this model or this invariant measure from this recently developed theory. Okay, for this model with Claudio, we have established some phase transition phenomena. We have proved some phase transition phenomenon in terms of stationary states. The main topic is about the mixing times for this model, but before going to the details, I'd like to explain you about this result. Okay, for this purpose, I need several notations, just one slide. Yes, let M plus be the space of all measures on the torus, whose total mass is bounded by 1. Because because we denote the empirical measure by pi n, and it can be viewed as a function on the state space with this value. So pi n is just an element of this set, and pi n can be viewed as a map like this. And as I said, mu n is just a unique stationary probability measure, which is invariant under the dynamics. And we also define another measure denoted by Pn. So Pn is defined by this formula. So Pn is just a pullback of mu n through the empirical measure pi n. Because mu n is just a measure on the space, and pi n is just a map from here to here. So Pn is a measure on this space. And in this slide, I can tell you our result, which have been established in this paper. And recall that the reaction term, F is the reaction term of the reaction diffusion equation here. And F can be computed like this, thanks to the particular choice of our jump rate. Yes. And of course, for our actual proof, we need some additional very technical assumption on C or macroscopic functions. But I'd like to avoid explaining it assumptions anyway. Anyway, we need some assumptions on C. And but anyway, F can be computed like this. So it is just a cubic polynomial. Yes. Okay. And then we have proved the following phase transition for our particle system. Okay, let us consider the high temperature regime, because if gamma is less than 1/2, then the potential becomes a singular potential. So in other words, the system belongs to the high temperature regime. So if gamma is less than 1/2, then the stationary state converge to the stationary state is concentrated on a single density profile, which is given by 1/2. Here it's 1/2. And on the other hand, if gamma is larger than 1/2, and let us define this alpha plus minus, and alpha plus minus are just zeros of F. So you can easily solve this equation. And its solutions are given by this alpha plus minus. Here is B plus equal minus F. Yes, and alpha minus and alpha plus. And we have proved that the stationary states are concentrated on alpha minus du and alpha plus du in the limit. Here, B delta denotes the delta open neighborhood whose center is alpha minus du in M plus. So the stationary state puts mass in the limit with equal probability, like this. Note that the potential is symmetric around 1/2. So we have equal probability like this. And so I want to explain some.
Kenkichi,
Sorry?
I have a question. May I ask a question?
Okay.
Yeah. So about this result. So do you need the in the proof of this theorem? Do you need the information about the symmetry of the potential to deduce that the probability is 1/2, or do you have an argument that allows you to compute these probabilities?
Yes, I think it's not essential, but for our proof, the symmetry is needed.
Okay.
Yes, but I think in general, if the symmetry breaks down, then the result changes drastically. Of course, let us consider if at this point, if it is degenerate, then it should concentrate on this point. I guess this is just my conjecture, but yes.
Okay, thank you.
Yes, in this sense, the symmetry is needed.
Okay,
thank you. Okay. Yes, and to prove this phase transition, we prove this is just a consequence of some large deviation principle I'd like to explain you in the following slides. So to prove our large deviation principle, we consider some diagram like this. So let me explain this diagram. So let n be a scaling parameter, and let us introduce the time horizon, capital T. And so this is our model. And as I explained you, if we fix T, and if we take n to infinity, then by the result by the Dumas Ferrari Lebowitz, the empirical density converts to the solution to the hydrodynamic equation, as I explained. But if we fix the scaling parameter n, and if we take n to infinity, then the distribution of this guy converts to stationary state Pn by the fundamental result on Markov processes. And we want to analyze this one. And okay, and let me mention this part. So for each solution to this hydrodynamic equation, if we take T to infinity, then the solution of this equation converges to one of these solutions of this equation. So in some sense, we naturally expect that stationary states converge to this one. But of course, this is and these are justified by letting T to infinity first and then n to infinity. And these are justified by n to infinity first and T to infinity. So in some sense, we need to interchange these two limits. And we should perform these interchange in the level of large deviations. So, and to study the large deviation principle corresponding to this part, we first study the large deviation principle corresponding to this part. And this has been done in our first paper. And after that, we followed Friedring and Wenzel's approach to study the large deviation, to prove the large deviation principle corresponding to this part. And actually, we have proved the following result. This is the main result of this paper. And we have proved the large deviation principle for the stationary state Pn. And sorry, I do not give you the precise definition of the rate function W, but the W is something like, if something like this graph on n plus, W should be like this. And it is symmetric and 1/2 to D. Yes. Yes. because this result is not so new, so I'd like to avoid the detailed explanation about this result. Anyway, the previous phase transition is a direct consequence of this result. Okay, and this is the main topic of this talk. So after this work, I have wanted to study mixing times for this model. So one can easily expect that at the high temperature, the system exhibits rapid mixing or fast mixing, and at the low temperature, the system exhibits exponentially slow mixing. So I have wanted to prove it, and I have wanted to know its proof, and we could do that. We could do this. Yes. So let us recall the notion of the mixing time for Markov processes. So mixing time is just is defined by this formula. So I think many of you know this definition, but let me explain again. So for each epsilon, the mixing time is defined like this. So we consider an infimum over time t satisfying this inequality. So let us consider the worst case eta. Eta corresponds to initial distribution of the process. So this is just a distribution of the process at time t, starting from the configuration eta, deterministic configuration eta. And mu n is just a stationary state, and we consider the total variation distance between two distributions, and we consider the time when this quantity is less than or equal to epsilon in this sense. So we take an infimum over t, which satisfies this condition. This is the definition of the mixing time, and as you know, this mixing time is very useful in the study of the Markov processes. But it is very, yes, as we know, mixing time for spin system is very interesting, but it's very difficult and very challenging, as we know. Okay, let me review two or several results on each marginal process. For the exclusion process, the mixing time for the simple exclusion process on the 1D segment or the 1D circle, 1D torus, the mixing time is of order n squared times log n, because there is no speed up factor. It is of order n squared times log n. And of course, much sharper result has been established by Uber and with his collaborators. And of course, yeah, as you know, he and his collaborators have obtained a cutoff profile, so-called cutoff profile for this, for the mixing time for the exclusion process. And we also know much more sharp result for the Glauber dynamics. But anyway, the order is important in this talk. So the mixing time for the Glauber dynamics is of order log n. And of course, the cutoff phenomenon has been proved in this very famous paper by Lebowitz. And but obtaining this order is not a hard task, and you can easily find in this monograph. But I'd like to emphasize that this is valid for any gamma, because for the 1D Glauber dynamics, the phase transition does not occur. So this is valid for any gamma. Yes. This is the introduction of our, these are previous work of our research. And this is our main results. So the first one is due to joint work with my collaborator Kenkichi Tanaka, and the latter one is recent work which is published from Alea very recently. Okay, the first one is on the high temperature regime. And and this is the real case. Okay, let us assume that the gamma is less than 1/2. So anyway, for this case, the mixing time is of order logarithmic of n. So in other words, fast mixing, the system exhibits fast mixing or rapid mixing. Of course, I can tell you some specific value of C0, but it's not important in this talk, so I'd like to avoid it. Anyway, the fast mixing occurs for the high temperature regime. And for the low temperature regime, we can say that the mixing time should be exponentially large in this sense, because there is a potential role. So anyway, but we need to prove it to obtain this result rigorously. Anyway, in this sense, I can tell you that this model exhibits phase transition in terms of mixing times. Okay, these are main results of my recent results. In the rest of my talk, I'd like to give you a sketch of these proofs. But this is just an intuition, so I do not touch detailed proofs. Okay, first let us consider the high temperature regime, or our single well potential case. But to go the microscopic dynamics, let's consider the macroscopic behavior of this model. So the macroscopic behavior is described by the reaction diffusion equation, as I explained you. And let us consider the worst cases. The worst cases must be given by this density evolutions. So this is just a solution to the hydrodynamic equation with initial profiles, with constant initial profiles, starting from 0 and 1. Because every solution should be sandwiched by these solutions, so 0, 1, 1/2, every solution should be sandwiched by these solutions. These must be worst cases. And because for this initial profiles, because these are homogeneous, spatially homogeneous, the Laplacian vanished. So it is just solution of the ODE at each point. So we can easily prove this exponential convergence. So it converges to the bottom of the potential. Wow. So this is an easy exercise for graduate students. And so, of course, if we take this C, then this discrepancy is less than or equal to 1 epsilon. Yes, this is just a macroscopic observation. So we want to perform this argument in a level of microscope. We want to perform this argument in a microscopic level. So we want to perform a microscopic version of this argument. This is our basic strategy to obtain rapid mixing or fast mixing. The corresponding worst cases should be given by this D0 and D1. So D0 is just the 0 configuration, and D1 is just the 1 configuration. And let us start the process from these two worst cases, and let us denote by GZTN and ZTN like this. And recall the CX theta is our jump rate for the Glauber dynamics, and sorry, I do not explain the attractivity more precisely, but CX is not bad, and CX is attractive in some sense. And by this attractivity, we can construct a monotone coupling between these two chains. So this is a Markov process, and each marginal evolves as a reaction diffusion model. And we also have this stochastic, we always have this stochastic domination. So we can construct this monotone coupling between these two chains. Yes. So we use this coupling to study the mixing time. And for this monotone coupling, we can define a coupling time denoted by tau n. And tau n, this is the first time when two processes meet. So this is the first time which satisfies this condition. This is the usual definition of the coupling time. And using this tau n, we have this general proposition. So the message is the following. So if we have the control about the coupling time, so Tn epsilon is a deterministic time we give it. So if we have the control about the coupling time, then we have an upper bound for the mixing time. So we use this general proposition. So the problem is reduced to studying the coupling, the probability of the coupling time. So to analyze this coupling, to analyze this probability, we consider the discrepancy between these two configurations. Because due to this stochastic domination, zeta is always larger than UZ. So this is nothing but the discrepancy. This is nothing but the discrepancy between these two configurations. And note also that if dnt equals 0, and then t should be larger than or equal to the coupling time tau n because of the definition of tau n. So in other words, we have this equivalence. Yes. So we are interested in this probability, and this probability it can be rewritten in terms of the discrepancy, and this is bounded by the expectation of the discrepancy by the Markov inequality, and this is just due to the definition of the discrepancy here. So we multiplied by n and divided by 1, divided by n. Yes. And this is a summary of the previous slide. We have this inequality, and note that this term is written in terms of the empirical measures for zeta work z, and because each marginal evolves according to the reaction diffusion model, the original process, and its macroscopic behavior is described by the reaction diffusion equation. So this is very non-trivial part, but we may replace these quantities by macroscopic quantities. But as I explained you, we have an exponential convergence for this discrepancy. We have this inequality. So we get this bound, for the probability on the coupling time. So if we choose a property, then we can say that by this proposition, we can deduce this bound. So the mixing time should be of order log n. But as you see, the main part is here. It's extremely non-trivial. But so this is the main part of our paper. But to overcome this difficulty, we need to go back to the original idea of the Masi, Ferrari, Lebowitz, and we construct many couplings to prove quantitative local algorithmic or local algorithmic replacement lemma. So this is a fundamental structure of our proof. Okay. In the rest of my talk, I'd like to explain you a brief intuition for the exponential slow mixing. Okay, let us consider the low temperature regime here. So in this case, V is double potential. B prime is minus F. This is a graph of B. But this is not a graph of B. This is a graph of W, which is a rate function for the LDP of Pn, of the stationary state. So in some sense, this W is a double potential in some infinite dimensional space and plus. So to prove exponential slow mixing, we construct several regions like this, alpha minus and alpha plus. And this is a, the A minus and E minus are neighborhoods of, A minus. Alpha minus du, and here is alpha plus du, and here is, what about du? But for this result, we don't need our symmetry for around 1/2. Yes. Anyway, so to prove exponential slow mixing, the following estimate is key. So we consider an exit problem from E minus, starting from A minus. So whenever the process starts A minus, then we can say that with high probability to escape from E minus, the process should wait exponentially long time in this sense. So the first time of pi n from this domain is exponentially large with high probability. So we can prove this result. And so we can prove this estimate. This is a key estimate to prove the exponential slow mixing. And the important thing is that here, H0, okay. So H0 is the height of this potential wall. H0 is here. But to state H0, we need to recall the definition of the dynamical, the rate function for the dynamical large deviation principle. So let us again fix the time horizon capital T, and let D be the path space, and we introduce this variational formula. So JG is so for each test function G, and for each trajectory density evolution pi or rho, we define this test function. Sorry, this functional, and we take a supremum in G. So this is a large deviation functional for from hydrodynamic limit. This definition is a bit rough, but essentially this is a large deviation net functional for the hydrodynamic limit. By using this IT, H0, the height of the potential world is defined by a variant of the so-called quasi-potential. So this is a definition of IT phi. So in this infimum, phi runs over trajectories and all time horizon capital T, which starts from a minus and ends up the complement of E minus. And we take the infimum over these constraints. So this is the definition of the height of the potential wall. Then to prove the exponential slow mixing, we need one more result, but this is stated for general case. As I explained you, the stationary state concentrated on alpha minus du or alpha plus du. But for general cases, we can say the following. For general jump rate C, we can say the following. And it is established in this paper. So let MS be the set of all stationary solutions. So rho bar is a stationary solution to the hydrodynamic equation. If there is a time derivative, it is nothing but the hydrodynamic equation or the reaction diffusion equation, but we don't have a time derivative. So this is a stationary solution to the hydrodynamic equation. And the hydrostatic limit tells us that stationary state is concentrated on this, or concentrated on all the set of all stationary solutions. So by this result, in the limit for some stationary solutions, for the set of stationary solutions, stationary states have put positive mass to the stationary solution, and we need exponentially large time like this. So by combining these two results, we can easily say that the mixing time is also larger. It should be exponentially large like this. Yes. And we show this estimate by following Friedring and Wenzel's approach in our infinite dimensional setting. Okay. Let me summarize my talk. So first, I have explained our previous result. I have explained phase transition for this model. And it is a direct consequence of our large deviation principle, which have been established in this paper. And after that, we have studied this phase transition in terms of mixing times. And in the high temperature regime, the system exhibits rapid mixing, log n order mixing, and in the low temperature regime, the system exhibits exponentially slow mixing. So it should be larger than E to NH0. Yes. And we conjecture these, we have many works. This is just a starting point of works, because I'd like to emphasize that the reaction diffusion model should be near to the Curie-Weiss model in some sense. So this is just our conjecture, but we feel this. Yeah, we think that these models are very similar. So these were proved for Curie-Weiss model. So we conjecture cutoff occurs for the high temperature regime, and at the critical case, the mixing time should be of order polynomial. The mixing time should be a polynomial order, and we conjecture that the mectastability holds for the low temperature regime these are our conjectures. So we have several future works. But anyway, if you are interested in these works, if you help me, I'm very happy. Okay, I'd like to finish my talk. And thank you for your attention.
Thanks very much, Kenkichi, for a very nice talk. Could I ask if there are questions from the audience? Maybe I could. Yeah, go ahead, Milton. You have a question?
Yeah. Thank you.
Hi, Minto. Yeah.
Hey, thank you very much for your talk. It was it's very nice work. So, okay, I don't want to be misunderstood, so I have to point that. So I read the Masi Ferrari Lebowitz in detail, and I know that it's really a huge work to prove this
Yes.
this correlation estimates. And
Yes.
so my question is, in this main part that you marked there, this quantitative local ergodicity, is just doing the Masi Ferrari Lebowitz, or you need something else? I mean, with just the Masi Ferrari Lebowitz, it means a lot of work, a lot of couplings, and it's super hard work. But it's basically all are basically these ideas, or do you need some additional input?
On additional input, yes. We have rewritten everything in a quantitative way. So to prove to obtain a quantitative estimate, we should rewrite everything. So that's our contribution. I know. Yes, we rewrote everything.
Okay.
Yes.
And
that was a hard work.
Yeah, no, I know it's really it's very hard work. I mean, I did these computations once, and that I know that they're not trivial at all. Okay, so another question. Okay. So with Patricia, we recently proved for this model that a CLT for the invariant measure. And so
you are talking about the dynamical one or the statistical?
No, for the invariant measure.
I mean, okay.
I mean, the idea is the same as you explained. You know that you prove dynamical CLT.
I see.
Then you take, and then you justify the exchange of limits
for the. I see.
And so the question then is knowing. So now we have a very precise description about the invariant measure. So knowing this very precise description about the invariant measure, can you get better results or not necessarily?
Okay. Yeah, maybe. So we don't know the explicit formula for the invariant measures. Yeah, sorry, I'm not sure, so I don't know what the.
Is that a question about the rate of conversions?
Rate of conversions over the for what?
For the CLT or
for the CLT?
Just yeah, Milton, you might also answer.
Yes, no, yeah. Now we have rate of convergence for the CLT, yes.
Even if you don't know the explicit formula for the invariant measure?
Yeah.
Very nice.
Well, maybe we can discuss about that. But I think that that were my. I think that were my questions for the moment.
So sorry for not answering to you.
Okay. No, it's okay. I mean, it's part of the discussion. No, so they're more like they're more like discussion questions than precise questions. I mean, it's.
I see.
So I didn't get Kenkichi. is this H0 that the bound that you get for the mixing time, do you expect it to be the correct rate? I mean, or is it just a bound on the mixing time? Because in order to prove the metastability you were mentioning, you will need exactly
Yes.
the right value.
Yes, of course. This H0 is not the correct one. So the correct one is something like this, and I cannot draw nice pictures. So maybe, and there is a lower landscape like this. Here, there is another saddle point, and here is 1/2 du, but there is another saddle point in some case. So the correct height should be here. This is how to say, this point corresponds to the instanton of the, yes, in some sense, in some case, this should be a correct, this should be a correct height, but in some case, this should be a correct height, I think, because this is a lowest, in some sense, it should be a lowest saddle point, I think, because this is a, yes, I think this can, I'm not sure this can answer to you, but I think I can capture a candidate or natural saddle point, I think. So this should be a saddle point to capture metastability.
Okay, and but you won't have an explicit formula for H0, right? For the exponential time you need in order to cross that.
Yes, but at this moment it is only given by the variational formula, something like this. Something like this. I'm not sure this is enough for proving the metastability or not, but I'm not sure.
Okay.
Yeah.
And when you say metastability, what do you mean exactly? Just to compute the transition time, or to prove that you are converging to some
yes,
Yeah,
no, just the hitting time. Starting from this point, the hitting time converts to the correctly scaled hitting time converts to an exponential variable.
Okay.
So I do not mention about the Iron-Cramer formula, etc.
Okay.
But I think the remaining thing is to prove the loss of memory property. So around this point, around the local, around the metastable, one of metastable values. So this might be done by combining our results, because we just performed for single value case. So if we can perform our same argument for a double potential case, then I think we can prove a loss of memory property. Then I think it should be enough to prove the metastability in the sense I mentioned.
Okay.
I feel it.
Okay, thank you. Very nice talk.
Yeah, thank you very much.
So Kenkichi, maybe just a quick one before. So if you have more than 2 wells, I guess that you can handle that also, right?
Yeah, of course we can work on. Of course we can work, but for the simplicity of the presentation, I focused on 2-way cases. 2-way case.
Okay, thank you very much. Are there any further questions from the audience? Okay, well, Kenkichi, I know it's very late at night. Thank you for coming on.
Yeah, it's AM 2 o'clock.
2 a.m. now.
But I'm very happy to meet you.
Thank you so much for giving us a very nice presentation and discussion. And so perhaps we can thank him again, and we can meet next week. Thank you very much.
Thank you. Good night.
Thank you.
Thank you.
Thank you.
Thank you.
Sorry
bye-bye.
for. Thank you very much. So I'd like to leave. I'd like to go to bed.
Happy dreams.